Data structures. Google searches 30 trillion pages in 0.2 of a second. Your app crashes with 100 users. The difference? About 47 lines of code and the concepts you're about to learn. That gap isn't about hardware. It's not about money. It's about how you organize your data, and that's exactly what we're covering in the next 20 minutes. Think about your context. You've got thousands of names in there probably. Tap one letter and boom, instant results. Not fast, instant. Zero perceptible delay. How is that happening? Well, that's a data structure at work, specifically a hash table, but we're getting ahead of ourselves. 4 structures, that's it. Master these 4 and you'll understand 90% of what powers the fastest systems on Earth. Arrays, hash tables, stacks and queues, and trees. Let's start with the simplest one, the one that's probably causing half your performance problems right now. Arrays are just boxes in a row. Numbered boxes, box 0, box 1, box 2, that's it. Your computer knows exactly where each box lives in memory. But here's where arrays betray you. Want to insert something in the middle? Disaster. Every element after the insertion point has to scoot over. 1 million items after your insert? That's 1 million move operations. O of n, linear time. Brutal. Same problem with deletion. Remove something from the middle, everything shuffles back to fill the gap. So arrays give you instant access by indexed, but terrible insert and delete performance. That's the trade-off. And understanding trade-offs is what separates good programmers from great ones. Now, here's where it gets interesting. What if we could get O of 1 for searches too? Not just access by index, but finding any value instantly. Hash tables are the cheat code of computer science. They turn any key into an array indexed. A name, a number, an entire document transformed into a simple indexed in constant time. Watch this. Alice goes through the hash function and becomes 3. Bob becomes 7. Charlie becomes 1. Each key gets its own address, like a postal code for data. Now, finding Alice, same process. Hash the name, get the index, jump straight there. No scanning through the list, no comparisons, only one operation. But wait, what happens if 2 keys hash to the same index? Bob and Bill might both map to bucket 7. That's called a collision. Oh no! There are a couple solutions. The simplest is chaining. Each bucket holds a tiny list instead of just one item. Bob and Bill both live in bucket 7. Chain together. With a good hash function and proper sizing, most buckets stay small. Search is still effectively O of 1 on average. The math works out beautifully. Hash tables power everything. Every dictionary in Python, every object in JavaScript, every database indexed. Spotify uses them to find your playlists. Netflix uses them to track what you've watched. Well, is there a trade-off? In hash tables, there's no ordering. So hash tables scatter data everywhere. If you need sorted data or range queries, you need something else. But for pure key value lookup, nothing beats a hash table. Now we've got random access with arrays and instant lookup with hash tables, but what about when order matters? When you need first in, first out, or last in, first out? Stacks are simple. Last in, first out, like a stack of plates. You can only touch the top. Add to the top, remove from the top, that's it. Your browser's back button, that's a stack. Every page you visit gets pushed on, hit back, and you pop the current page off, revealing the previous one. Your undo functionality in every app you use, that's a stack. The call stack that tracks function calls in your code, that's a stack. They're everywhere once you start looking. Now, queues are the opposite. first in, first out. Like a line at a coffee shop, the person who arrived first gets served first. Every print job you sent goes into a queue. Task scheduling in your operating system uses a queue. Web server requests lined up in a queue. Both stacks and queues are O of 1 for their core operations. Push, pop, and queue, dequeue, all constant time. No scanning, no searching. But there's a limitation. Arrays give random access, hash tables give key lookup, stacks and queues only let you touch the ends. What if you need everything, like fast search, sorted order, and efficient insert? We'll want to be looking at trees. Trees are hierarchies. One node at the top, the root. Each node can have children below it. Those children can have their own children. It's turtles all the way down. The magic happens with binary search trees. Each node has at most 2 children, and here's the rule. Everything smaller goes left, everything larger goes right. Watch what happens when we search. Looking for 63, start at 50. 63 is bigger, go right, hit 70. 63 is smaller, go left, and just like that, we found it. 3 comparisons instead of 7. That's logarithmic time, O of log n. Every comparison eliminates half the remaining tree. A billion items? About 30 comparisons. That's the power of logarithms. Insertion works the same way. Find where the new value belongs following the left-right rule and attach it there, O of log n. Deletion is a bit trickier but still logarithmic. Now, trees give you sorted order for free. An in-order traversal, left, root, right, visits nodes in sorted sequence. No extra work needed. This is why databases love trees, specifically B-trees, a variant that's optimized for disk storage. Every time you query a database, trees are doing the heavy lifting. The catch with basic BSTs, they become unbalanced. If you insert sorted data, you get a skinny tree that's basically a linked list, O of n again. That's why we have self-balancing trees, AVL trees, red-black trees. They automatically rebalance after every insert and delete. Guaranteed O of log n, always. Alright, thank you for watching. If you found this helpful, hit that like button and subscribe for more deep dives into the hidden mechanics of computing. I'll see you in the next video where we'll explore even more ways to squeeze every last drop of performance from your code.